Good morning, everyone. This is discussion 2 on mole calculations, and I've been asked a few questions. So we are going to look at 3 different questions today. The first one is from the November 2018 question paper. We are not going to look at the basic acid-base questions. We are going to move right on to 7.3. Now here they tell us that water in a certain lake has a pH of 5, and then they ask us calculate the concentration of the hydronium ions. Now we did a lot of that. I actually don't want to spend time on this, but we need this. So let's quickly write it down. So the pH would have been, having the equation is important, then 5 is negative the log of the H3O plus concentration, and then when you work it out, it will be H3O plus concentration is just 10 to the minus 5, or you could have preferred to write 1 times 10 to the minus 5. That's also correct. Right, so that was just because we need it. Now we get to the question. Now that is the water in the lake. It's a little bit acidic. And now what they tell us, the volume of the lake is 4 times 10 to the 9 cubic decimeters. And they take lime, calcium oxide, and they added that to the water to neutralize the acid. It was a little bit too acidic, and they added calcium oxide to neutralize it. But what's very important, they give us the equation, but it is not 1-to-1. They did not completely neutralize it, right? They neutralized some of that. And how do I know that? Because when they continue, they say the final amount of hydronium ions is. So this is excess. It's after the reaction, right? The final amount after reaction is an excess. So immediately that will tell me how I'm going to approach this. And the question is now, calculate the mass of the lime. So I'm looking for the mass of the calcium oxide that was added. So since I'm working with an excess, I will prefer to keep book of what did I put in, what reacted, and what was in excess. And they are now asking me, what is this mass, right? I will get that by working out the moles first, and the moles that react of this one will tell me how many moles of this one react. Right. Moving on, let's see what they gave us. They tell us the excess, right? So here the excess is 1,26 times 10 to the 3. They gave us that in the question. And now I want to know, what did I put in? Now, I put in the whole lake, right? So that was a volume of 4 times 10 to the 9. And the concentration of the hydronium ions I've already worked out over there, 10 to the minus 5 moles per cube decimeter. So that's going to tell me what I put in. Then I'm going to use them to get whatever reacted. And that will tell me how many moles of calcium oxide reacted and give me the mass that they've put in. So first off, let's start there. Concentration is moles divided by volume. Concentration 10 to the minus 5 now. Moles, I'm looking for volume 4 times 10 to the 9th. So that is telling me 4 times 10 to the 4th mole, and that is the H3O plus that I put in. Right, so it's over there, 4 times 10 to the 4th. That is how many moles I put in. So what reacted? Well, the moles that react is therefore the moles that I put in, 4 times 10 to the 4th that I put in, minus the 1,26 times 10 to the 3 that is left over, the ones that are in excess. And when you subtract that, you end up with 3,87 times 10 to the 4th mole. And that is now the H3O plus that react. Right. Now I'm working from there to there. Now from there to there is a ratio. So I have to say calcium oxide always react with H3O plus in the ratio of 1 to 2. Right. And I know how many of the hydronium ions. There's 3,87 times 10 to the 4th. I am looking for this. That will just be divide by 2. And if you divide by 2, I end up with the moles of calcium being 1,94 times 10 to the 4 mole. Right. Okay, so now we've worked out the mole. The only thing left is to convert mole to mass. All right. So we're doing N equals M over M. I know the moles, 1,94 times 10 to the 4th. And that is the mass that I'm looking for divided by the molar mass. And we're working with calcium oxide. So it's 40 plus 16 to give it all together 5, 6. And when you do that, you end up with a mass of 1,09 times 10 to the 6. And that will be grams. Right, so the moment that you see something is in excess, be aware that you will need to subtract the excess from what you put in order to get the number of moles that reacted, so that that can give you, with the ratio, the number of moles of the calcium oxide. So guys, that was the first question. Right, for the next question, we're going to look at the 2019 paper in July, and we are not going to do everything. We're moving right up to 7.4. Right, a learner wishes to identify element X in hydrogen carbonate. Right, to do this, she dissolves 0,4 grams of the XHCO3 in 100 cubic centimeters of water, and she then titrates all of the solution. That is important. Everything is being used with a 0,2 moles per cube decimeter hydrochloric acid solution. Methyl orange is used as indicator during the titration. Right, we are not going to look at 7.41 and 7.42 basic acid things that we did in the previous topic. Right, we are going to move on and do the mole calculation. Right, and now they tell you at the end point she finds the 20 cube centimeters of the acid neutralized. What does that tell you? In the right ratio, right? In the right ratio. All the hydrocarbonate, the balanced equation is this, and then identify element X. Now let's start by seeing what they gave us and what we need to work towards. We have XHCO3 and we've got HCl, and that is going to react, and it is already balanced, right? Now, what do I know? I know of the XHCO3, they gave us a mass of 0,4 grams, and the volume over there, 100 cube centimeters, right? And then she titrates it with this, and they give us the concentration, 0,2 moles per cube decimeter, and then they tell us at the end point, so they gave us volume there as well, 20 cube centimeters. And since it's at the end point and they have fully neutralized, I know 1:1. So this can give me the number of moles of HCl. That can give me the number of moles of this one. And usually if they asked mass, we would have worked this out then from that mole. So this would have been N equals M divided by molar mass. And usually we know the molar mass because we know the substance and we're looking for the mass. But this time we know the mass, we're looking for the molar mass. Right, so we're first going to calculate the moles of HCl. That will give me the moles of XHCO3, and then I will use it in this equation to work out the molar mass. And if I know the molar mass, then I can start looking for X. Right, so let's start first with that concentration. So the concentration is 0,2 and the volume is 20 cube centimeters. So that will be 0,02 to go to cube decimeters, ending up in 0,004. And that is now moles of HCl. Right. So I've worked out the moles of HCl. Next up, from there to there, right, I've got XHCO3 to HCl. They are in the ratio 1:1. 1 mole of this will always react with 1 mole of that. So immediately that tells you that the moles of XHCO3 will also be 0,004 moles. Right. So now I'm up to there. Next up, I'm going to use my equation N equals M over big M. Right, moles 0,004, mass 0,4, and molar mass is the only unknown, and that gives you 100 grams per mole, right? Grams per mole. So now at least I know the molar mass of this. Right, so let's look at XHCO3. Now that part is a negative ion, right? Carbonates 2 minus, hydrogen 1 plus, or you can work with them all together. The actual fact is they are negative. And that tells me this must be a +1. So it's not something in group 2, it must be something in group 1. Now, if you look at group 1, first in the group is hydrogen, and it's obviously not hydrogen. So let's look at the second one in group 1, and that will be sodium. So if you look at sodium bicarbonate and you calculate the mass, that will be 23 plus 1 plus 12 plus 3 times 16. And if you do that, you end up with 84 grams per mole. So obviously, it's not sodium. It doesn't give us the 100 grams per mole that we're looking for. Next up in group 1, you will find potassium. So if we work out the molar mass of potassium, H2, that will be 39 plus 1 plus 12 plus 3 times 16. And if you do that, you end up with 100 grams per mole. And that is what I am looking for. So immediately that tells me X will be potassium. Now, the last question we're going to look at today comes from November 2017 paper, and we're not looking at the whole acid-base question. We're only looking at the one that requires a lot of mole calculations. In a laboratory, a technician wants to determine the concentration of a hydrochloric sample. He adds 5 of that sample to 495 cube centimeters of distilled water to give a total volume here of 500 cube centimeters, and that is now the diluted acid, right? And then to give 500 of diluted acid, and then during a reaction only 50 of that 500 is used, and that reacts completely with 0.29 grams of sodium carbonate. And they give us the reaction. Now, reacts completely tells me over here they are in the right ratio. They reacted completely. They reacted in 1 to 2 in that beaker, right? So we can work easily with that, but then let's think about what's happening here. Now, first off, when you dilute something, you only add water. So the number of moles that you put in here, the initial or first number of moles, will be the number of moles in the solution after dilution, because you only add water. The number of moles of acid you put in are the number of moles afterwards. You didn't add any acid, you only add water. So the moles you put in equal to the moles in the whole solution. Right, but then we do this. We take from the 500 cube centimeters, we only take 50 cube centimeters. Now, first off, let's think about the concentration. Now, the concentration in this beaker is actually the concentration of the HCl that we put in there. They are equal, right? But what happened when I take from the 500, I only take 50. So the volume, I only take 1/10 of that total volume. It means I only take 1/10 of the moles that I had over there. Remember concentration, mole per volume. This one is now the constant, right? It's constant. It's not changing when I put it in there. But I am, from the original one, I am taking only 1/10 of that. So I'll only have 1/10 of the moles as well. Right, so there's 2 ways that you can approach this. First off, you can work out the concentration of what you put in and say, but that is the concentration in this beaker because they are equal. Or you can work out the moles over here, but then you have to remember that I started off with 10 times that, right? And then you can work with the dilution. So I like to work with moles, right? Because then you don't have to worry too much about when the concentration change. So let's start by looking at this reaction. N2CO3 plus 2HCl. They gave us this reaction and it was already balanced. Right. Now, they reacted completely, so I know they are in the ratio 1 to 2 when they react. And they give me the sodium carbonate, they give me mass of 0.29 grams. So I'm going to convert this to moles and then get the number of moles of HCl over there, right? And then I will multiply it by 10 to get the number of moles in this beaker. So once off, let's start with that one. So N equals mass divided by molar mass, and that will be my 0,29 divided by, I'm working with sodium carbonate, 2 times 23 plus 12 plus 3 times 16, I end up with 106. Right, and if you do that, you end up with 0,00274 moles of sodium carbonate, or 2,74 times 10 to the minus 3. You can write it out like this, just don't round it off, don't round it off, and just keep this in your calculator as well. Right, so we have worked out the number of moles of sodium carbonate. Now I'm going to work out the number of moles of hydrochloric acid that react with that. So we're going from sodium carbonate to HCl, and this equation tells me 1 mole of this will always react with 2 moles of that. So if I have 0,00274 of this reacting, how much of that will it need? It will need double that, and double that is 0,0547 moles of HCl. Now, what's important? That is what I put into the last beaker, right, into the last beaker. Right, so, but what do I know? The moles, when I took only 1/10 of the volume, I only took 1/10 of the moles. So if I want to go back, I have to multiply. So there is 10 times 0,00547, which is 0,0547 moles of HCl in the second beaker. Right, and now what do I know? I diluted it, right? Which tells me that the moles that I've put in are equal to the moles in this beaker, right? I've worked out the moles in this beaker. That will be equal to what I put in, and I know the volume I'm asking for what the concentration that I put in. So C equals N over V. I know the moles in that second beaker, 0,0547, is also the moles that I put in. The only thing that I added was water, right? And now the volume. And the volume that I put in was 5 cube centimeters, so that would be 0,005. And if you do that, you ended up with a 10,94 mole per cube decimeter concentration. Right. So I like to work with the moles, working out the moles and then multiply by 10 to get the moles over there, and that is also the mole that you put in there. Right, or you could have chosen to, once you've got there, to continue from there, and then from there to get, instead of stopping and working with the moles, you could have gone on to concentration, right? So let's do that one. So here you would have said C equals N over V. I've got my 0,00547. Now I am in the last beaker, so the volume I'm working with is 50 cube centimeters, 0,05, and that will tell me I've got a 0,1094 mole per cube decimeter. And what is that now? That is the concentration in that last beaker where we did this, which was the concentration that we took over, right, in the last beaker. But remember, we said the concentration didn't change, right? The volume and the moles that we took from here changed, but the concentration stayed the same. So that is actually the concentrator that we put into the last beaker, and that is also the concentration in the second beaker, right? The diluted one. So we now have the concentration over there, and they're asking us for the original concentration. And then I'll say, okay, but this is just dilution. So when you dilute things, you add water. The moles that you put in are the moles that you have at the end. So that will be C times V is equal to C times V. Right. The concentration that I started off with, the sample, I don't know. That's what I'm looking for, that concentration that I put in. The volume that I put in was 5 cube centimeters. And then afterwards, the concentration over here, now that was what I put in there. Remember, it stayed constant, and that was 0,1094. And the new volume over there was 500 cube centimeters. Right. So if you do that, you end up with 0,94 mole per cube decimeter. So that was the other way around. So when you take just a part of that solution, it means the concentration here and there stays the same, but since the volume changed, the amount of moles will also change. Right, guys, I hope that helped a little bit. Next week, we're going to start looking at maths in physics. So if you've got problems knowing what the shape of the graph should be, or if you don't know when to use the gradient or the area underneath the graph, make sure to watch Maths in Physics.